Welcome to our lectures on the DC microgrid and the control. We are discussing in previous class on the passive damping of the microgrid stabilization. Now, we shall discuss about impedance and the admittance criteria for the stability of the microgrid. Now, the small signal stability, where it is related to the small perturbations of one entity or various entities. The small signal stability of a DC microgrid system is related to the small signal impedance of the source, load and the network systems. So, these are all entities we will cover once you have a small changes in irradiation level. So, your effective impedance level, impedance point will change, and load may also change little bit. Huge change in load, of course, it will come under large stability at large. So, and the loads and all those system has to be considered here. The impedance of the source in DC microgrid is usually considered to the resistive, because inductance does not have any effect here, and unlike the conventional gate where x by r ratio is around 7. So, predominantly you have the inductance, but in case of the DC microgrid you do not have any inductance, induction is shorted. And for this reason, predominantly what we mean by this impedance is the resistance, and the positive small signal impedance because of the droop characteristics. Generally when load increases, you will find that the bus voltage drops. So, for this reason you have the droop characteristics. And also load can be classified, we have discussed several times before also. Constant power load, this is the quite nasty kind of load, and also constant current load, it takes constant amount of current irrespective of the battery charging kind of applications maybe, and the constant impedance load, and that is the good load. Why? If you change the voltage, then current drawn will be different, and if you have increased the voltage, current will be more, and thus you try to stabilize the DC bus, and the reverse will happen, it will track less current, and thus it will try to stabilize also that DC bus. And generally, but what we can say here, but usually a load behaves as a mix of this three types of load, and in a microgrid we require to see which load dominates. If CPLD dominates, then control has to take care of it, and if the impedance load dominates, you have a little leeway. So, control will not be that challenging. The load in the DC microgrid that are predominantly constant power load have the negative small signal impedance, because once its voltage decreases, current increases, and thus dVdi is negative. So, for this reason you had a problem, that is a negative small signal impedance. The combinations of badly scaled positive and the negative impedance in the same system cause a small signal impedance. You may have a load which is as a positive impedance coefficients, and another due to the CPLD you have a negative resistance, and they will interact, and thus it throws the system out of gear. In the context of this microgrid, stability may be examined by computing the loop gain transfer functions of the regulated system of the power converter that form the network. the power electronics based power distribution systems, in abbreviation we say that it is PDES, are becoming increasingly common popularly at the marine and the aerospace applications. We have a submarine that require a DC propulsion and all those things. In submarine it can be visualized because it has a huge battery bank. So, it can visualize itself as a DC microgrid. Same way as spacecraft, an aircraft. So, that can also be visualized as a isolated DC microgrid in islanding mode when it is flying. So, their stabilities are the very big challenge, these two entities or the ship. The stability analysis of this class of the systems is crucial due to the potential negative impedance instability. So, CPLD is the hazard, and thus what you require to do, these power electronics distributed systems can offer excellent load regulation. So, we require to manage this thing by this power electronic switches, and the transient performance and the proper architectures, a high degree of fault tolerance, because CPLD has to be there, then it should cause the negative impedance to come into the pictures, and since voltage goes low and thus it will track more amount of current, and therefore, this reason to restrict those we require this power distribution systems. Now, we shall discuss what is our content is today. The most stability analysis of this PDs is based on impedance admittance method. So, we prefer generally impedance method, that is a part of the series resonance analysis, and also we may have admittance method, we have parallel resonance. This methods based on the fact that small signal stability at a given operating point can be determined by examining the Nyquist contour of the product of this source impedance ZS and the load admittance, that is YL, in a single DC bus system. Of course, these things becomes quite complicated once you have we have studied different kind of architecture of the DC microgrid, and that will be a different area, but we take the simple case, that is a single bus system. The most common methods of this impedance admittance criteria is, we have referred this Middlebrook criteria in our previous discussions also, which states that the system will be stable provided that the Nyquist contour, that is ZS YLs, remains within the unit cycle. That is the one of the requirement. And to satisfy that, what we require to do, the primary disadvantage of the Middlebrook criteria is that it leads to an artificially conservative design. So, you will find that unnecessary you are putting extra damper to ensure the stability and efficiency will be poorer, and we require to revisit this criteria, this Middlebrook criteria here again. The impedance based stability of a single bus DC power system can be explained using this figure 1, and this is the Thevenin equivalent circuit, and so this is the source impedance, and this is a load impedance, and this is the load voltage, where in this figure 1 Vs and Zs represents the Thevenin equivalent voltage and impedance of a linear source converter model, and VL and ZL represents the Thevenin equivalent voltage and impedance of the linearized load converter model, and this IS and IL represents the current flowing to the twist converter respectively, and we have considered a single bus system. And from this figure we can write that V, that is Thevenin equivalent voltage, is ZL by ZS plus ZL into Vs plus Vs Zs plus Zs plus into VL. So, it is convenient to define, let us say that Zs equal to, in the terms of the polynomial in a Laplace domain, that is numerator and the denominator. So, and so again it will be NL by DL. So, while substituting these 2 and 3 in 1, so we can find out V as NLDS into Vs plus NSDL into VL by NLDS plus NSDL. Assume that the load operates in a stable fashion. If supplied from the ideal source, NL will not have any zeros at the right hand side of the S plane, and thus the system is going to be stable. Similarly, assume that the source can operate in a stable fashion if supplying a constant current load, that is separately, at least in the small signal sense, then ds will not have any zeros at the right hand of the S plane. So, factorizing this term in the V, considering this criteria which we have stated right now. So, this equation 5 can be yield, and thus we can write V equal to NL into ds into Vs plus NSDL into VL by NSDS plus 1 Zs YL, where YL is the load impedance of 1 by ZL. Since neither NL or nor ds has any 0 in the right hand of the S plane, it follows that the interconnected system which was shown in the figure 1 is stable, and provided that 1 plus Zs into YL does not have any 0 in the right hand side of the S plane. So, that is the criteria required to be fulfilled. Now, then in a Nyquist theory, the coupled with the fact that neither Zs or YL have any pole in the right up plane, the number of unstable poles of the closed loop system is equal to the number of clockwise encirclement, that is the Nyquist criteria of at the point equal to minus 1 J0 made by the Nyquist contour of Zs YL. So, let us revisit that Middlebrook criteria once again. So, we have qualified and satisfied the Nyquist criteria, and this Middlebrook criteria tells this consists of a circle of radius 1 by Gm in the S plane, where Gm denotes the gain margin of your Bode plot. Please understand what we are saying today all are average model. So, we cannot cover the nonlinear integral nonlinear control, but students are requested to first introduce the linear control and see the stability, and if it is works fine, if you can design the system PID controller based on this average model, that also works fine. So, thereafter we can investigate the nonlinear control and find it out that what are the advantage of the nonlinear control. But for time being our concentration is totally on the linear control. And we know that there are different issues of the system gain margin, phase margin. If the Nyquist plot of ZSYL is always within the circle, then encirclement at the point minus S j 0, that is minus 1, cannot occur provided that this gain margin is greater than 1. That is something we require to keep in mind. The constraint has a merit in terms of the designing criteria, in that for a given the source impedance, the range of the allowable load impedance, load admittance, that is YL, readily established, and in particularly the load admittance, that is the mod value, should be less than 1 by ZL into GM. That is something we require to consider and required to be established. So, this is the stability criteria, this is the unity cycle, and this is the sigma axis, and this is the j omega axis. Now, in this method and opposing the argumenting criteria, we can say that in this method the Nyquist diagram is required to fall to the right side of the S line, that is equal to 1 by GM, the gain margin. This criteria has an advantage over the Middlebrook criteria. What is it? The criteria in that it can be less artificially conservative, because it allows the Nyquist diagram to occupy a larger region in the S plus. So, this lower circle, this lower circle is your Middlebrook criteria, and this one is the Isaac criteria, and this one is your gain margin, phase margin criteria. And you can see that you can very well operate. This is a Middlebrook criteria is a little conservative approach of the stability. You can very well operate this above cycle with a encirclement and having your stability criteria satisfied by the gain margin. So, by the Bode plot only we can ensure proper stability of the system. Now, the gain margin, phase margin criteria, let us visit that. Students are requested to revise your basic control theory to understand it better. This is also another approach which reduces the conservatism, or this that approach in the Middlebrook was restricted. This the design as depicted in the figure 2, that is the Middlebrook approach essentially. In this method the boundary consists of the two line segment at an angle of plus minus Pm. Please refer to the figure number 2, this is the figure number 2. So, this is the plus minus Gm, plus minus Pm from the negative real axis, which extend from the infinity to the circle correspond to the Middlebrook criteria. So, students are requested to take the snapshot or screenshot of this my figure number 2, so that they can correlate this statement better. This segment of the circle is connected, these two lines segment is apart of the this gain margin, phase margin boundary. the region of the indicated boundary is considered as your controllable boundary. And thus, what we can say is that selection of the stability criteria has considerable impact on not only the performance of the design, but also the design process itself. So, if you look from this side, this will be the source side and this will be the load side. And now, what happened? We have grouping the component. So, you have transferred this capacitor this side and see that what will be the changing occurring. And in order to illustrate the above statement, consider the two systems, that is the source side impedance and the load side impedance A and the B. First is the component grouping, first component grouping, that is the source and the capacitor is a part of the load, and here capacitor is a part of the source. Now, for the A, each of the case system is identical, but grouping of the circuit element into the load and the source differs. Essentially, capacitor is shifted in between the two entities. This circuit itself consists of an ideal voltage source with a series RL impedance, a negative resistance representing the dynamic linearizations of the constant power load, and the shunt capacitance, that is something we require to do. And thus what happened, upon writing the state equations of the circuit, it can be shown that the stable operation will occur when capital R is much greater than smaller, and this C is much better than the time constant, that is the L by RR. So, in that case we will consider it like that. So, what happened here? Let us revisit this condition once again. This is the source resistance and this is the load resistance, and our condition is that the load resistance, since it is a negative type because of it is the CPLD, and our consideration is that this load resistance is much greater than the source resistance, and this capacitor what you have, this value is this ratio L by R into R, and it should be greater than C. So, if you do that condition, then what happen in these configurations? So, then this interchangeability is possible, and for this reason in each case the system itself, though it is identical, but if this condition was not satisfied, then we cannot consider this case to be the identical, but grouping of this circuit element into the load and the source, here it will differ. And another point also, here the circuit itself consists of the ideal source, that you have to keep in mind, but in case of mostly in case of this in case of the microgrid, that kind of situation does not arises, because ultimately you have a solar entity, and thus you have a DC to DC converter, and it has got own impedance. So, it is a oversimplified model, but in this oversimplified model, if this criteria is considered, then this gain margin phase margin model will be satisfied, and what you have done in case of this Millbrook approach, that is a conservative approach you require to operate your model within this inner circle. Instead of that, you can go to the outer circle if you consider your system for the gain margin and the phase margin model. This is the one of the way of analyzing it, and of course, this model is totally linear and it has got lot of approximations, and we have considered only the load to be here negative. Thus, it is a constant power load, and this analysis may change or differ if you have a constant current load or the constant impedance load. But since more stringent condition arises once you have negative resistance, for this reason this example is been chosen, and where you have a CPLD, and students are requested to validate this whole system of PN, this phase margin gain margin method by other kind of constant loading, and you see that whether this control bandwidth increases or not. That is something we require to, once we have an online forum and all those discussions, we will take out these issues, because we cannot cover in the 20 hours all those aspects of the control. So, and students are welcome to revise all these control aspect, otherwise they will find it difficulty to understand this part of the microgrid. Thank you for your attention. We shall carry forward our discussion of the control applications of the microgrid, DC microgrid. Thank you.